Hello everybody, Mr. Chan here. I'm about to do a lesson for Algebra 1, topic 1-2. Grab your note takers. I'm about to do some notes here. 1-2 is called solving linear equations. And the opener is Joshua is going kayaking with a group during one of his vacation days. In his vacation planning, he budgeted $50 for a kayak rental. Most of us try to guesstimate or estimate in our heads how far $50 would stretch. If we just focus on a single kayak, we would probably add $15 and $15 and so on. And at some point we realize that we can squeeze 3 hours of a single kayak. 3 times 15 is $45, just under the budgeted $50. That's a single kayak. I hope you're riding along with me. Now, if it was a sea kayak, let's see what our limit is there in terms of the number of hours we can rent that one out. I think 2 is the most because at $36, 2 times 18, we don't have enough for another hour of single sea kayak. All right, that answers the first question. How many hours can you rent each type of kayak? And we described 2 different options. Single kayak for 3 hours and 2 hours for the single sea kayak. All right, second question. Joshua found out that there is a $25 non-refundable equipment fee. Oh boy, great. In addition to the hourly rates, how does this requirement change the mathematics of the situation? Remember, our budget was $50. We now have a non-refundable $25 fee. That will leave us with only $25 when you subtract the 2. Whoops. First mistake, ha ha ha. Which means $25 is barely enough to cover only 1 hour of each single kayak and single sea kayak. All right, moving on. How do the processes you use for parts A and B differ? How are they the same? Well, it's just a matter of using operations. Adding, multiplying, and subtracting. Okay, let's move on to the next page. All right. Now, keep in mind, your textbook has different examples than the one in your note taker. So before I start here, I want to remind you of something that we've learned about in your previous math classes, that you have from a different teacher, order of operations. Write that down off to the left-hand side. I realized when early on as a student myself, the acronym PEMDAS was a great way to memorize order of operations. For simplifying, we go a certain direction. Parentheses and exponents are first, multiplication and division are second, and adding, subtracting are last. Those are the operations that are important when you're simplifying mathematical expressions. However, this particular section is about solving. Solving is undoing order of operations, and we want to go backwards of PEMDAS. We're going to go add and subtract first, multiplication and division second, and parentheses and exponents last. Keep in mind, the way I wrote PEMDAS is referring to how each of those are important with each other from left to right. If you have multiplication and division, they're equally important, but you just work from left to right. You don't necessarily pick on all the multiplications first and then the divisions second, okay? It's always from left to right. All right, let's take a look at our try it problem. This is different from the book. You may use the textbook, example 1, to see how they do their problem. Their problem looks like parentheses and 2 times x plus 4. In the numerator and in the denominator, there's a divide by 3, minus 8 equals 32. Ours is different, of course. We have a problem where we're trying to solve. Solving is where you want to isolate the variable. In this case, our variable is the letter x. The letter x is buried up inside a fraction bar. Let me write the problem a little bigger so we can see it a little clearer. Keep in mind, when you're dealing with equations, there's an equal sign. So what I like to do is split the problem into equal parts, the left side of the equation and the right side. Now the variable is buried up here in the parentheses, in the fraction bar. And what you want to do is you want to undo operations because we're solving. The most important thing to undo are adding, subtracting. Now, if you look at the left-hand side, we have that 4 right there. There technically is a little sign in front of the 4. There's a little plus sign there. I can move it or make it go to 0 by applying the opposite of plus 4. In this case, I want to subtract 4 to both sides. Remember, this is a balanced equation. What I do to one side, I must do to the other side. 9 minus 4 on the other side, of course, is 5. All right. Our problem is a little nicer looking. Our variable x is still there. It's buried in the fraction bar. Now the thing about the fraction bar is everything in the numerator position, 3x minus 1, is in itself untouchable. You do want to get rid of the divide by 2 next. Opposite of division is multiplication. I'm going to go ahead and multiply both sides by 2. If I do it to one side, I got to do it to the other side. Bam. The 2's go away, and what am I left with? 3x minus 1 equals 10. Almost there. Wow. We still have to keep our eyes on the prize, and that's the letter x, that's our variable. We're now down to 3x minus 1. The fraction went away. We are now facing either getting rid of multiplication or subtraction. Now, according to my order of operations backwards, I do need to get rid of the adding subtract next. It's still more important than multiplication. So let's go ahead and do opposite of minus 1, which is plus 1 to both sides. Interestingly enough, I'm almost there. When I divide by 3, the last step, that will get rid of the multiplication by 3 with the x. My answer comes out to be a fraction. Oh no! And there's my answer. X equals 11/3. We have some time here. I'm going to go ahead and do the one from the book. Or not. Oh, I see what I did. Are there any questions? Everybody doing okay? All right. Question at the bottom there. How can you check that the value of the variable makes the equation true? What you want to do is substitute the value for x and check the answer. So our answer that we got was 11/3, and we would have to substitute 11/3 into the equation, the original equation. And I challenge you guys to try that on your own. All right, let's move on to something different. In this case, we have an interesting problem coming up, and they use the word, hey, solve consecutive integer problems. Consecutive means next to in math. Here are some examples I'm going to put to the side. Involving some consecutive integer sequences. Here's one. The one we grew up with when we were little kids. 1, 2, 3, 4, and so on. Hey, that works. Those squiggly marks that I've drawn there, that's called set notation. It just groups your set of numbers together, and the dot, dot, dot means it goes on forever. We have another one. What are these? Aha, those are odd integers. All right. Let's take a look at our problem here. The sum of 3 consecutive odd integers is 57. In math, the word is refers to an equal sign. So let's go and set that up. Is 57. Okay. Sum in math means to add. Great. We're going to add 3 values we don't know together to equal 57. Now, if you look at my first list there, 1, 2, 3, 4, those are consecutive integers. They are increasing by 1 unit. So I'm going to do something called assigning a variable. I don't know what the number is. Let's go and do that. X would be my first odd integer. Oh yeah. Keyword here is odd. My second odd integer is not 1 apart like my regular integers, but it's actually 2 apart. See how this goes? I could have given you the problem like in the first example, 1, 2, 3, 4, but in this case, it's 2 apart. So my second unknown odd integer relies on the first number, and the first number is 2 units less than the second integer. So I'm going to put a plus 2. That represents the second odd integer. Make sense? So there's 1 and there's 2, and we have 1 more to go here. That would be the third odd integer. Now, if they're 2 apart, plus 2, then if you have another 2 apart from there, it's plus 2 plus 2, that becomes plus 4. Make sense? Because if you look at the list over there on the left, 1, 3, 5, well, we have 1, plus 2 is 3, plus 2 is another 5. But relative to the first value, those right there are 4 apart. That's why I'm adding 4 over here on the right. This is our third odd integer relative to the first odd integer. And ladies and gentlemen, we've just created a algebraic equation. Congratulations. Now, some things I haven't mentioned yet that you should know from middle school are variables. Variables can be combined together, like they're called like variables. So here we want to do something called combine like terms. Or variables. I have x, x, x. Those can be combined together. How many are there? Well, Mr. Chan, there are 3 of them. So x plus x plus x is 3x. Then, of course, on the same side, I can combine the 2 and the 4. 2 plus 4 is 6. Bingo. We now are going to go ahead and solve this. Solving is undoing operations. When it comes to doing that, I need to undo adding, subtracting first. So I need to get rid of the plus 6 by subtracting 6 to the left and the right side. Aha, almost there. Last step. We have 3 times some number we don't know equals 51. Opposite of multiplication is division. All right. I don't know about you, but I do know how many times 3 goes into 51. That is 17 times. And there's your answer. Yay. Okay, let's move on to example 3. Now, these types of problems are not easy. They're called mixture problems. They are challenging. I'm going to change a couple of values on here that I would like to match up with the textbook. If the lab technician needs, let's change that 30 to 25 liters of let's change that 25% to 15%. Acid solution, how many liters of the 10% and the 30% acid solution should she mix to get what she needs? What we're doing is we're mixing 2 solutions that have different percentages. One with 10% and another one with 30%. The nice thing about these problems is that once you see a setup for one of these problems, it actually becomes very easy to see the combination of them. So we need to get a 15% solution of 25 liters. Now 15% needs to be converted to a decimal. The traditional way, of course, is to divide by 100 or move the decimal point 2 places. 15% is also known as 0.15. Now, when you want 15% of 25 liters, of means to multiply in math. Let's do the setup there. Ready? 0.15 of 25 liters will give you what you need for one side of the equation. Okay? What are we mixing? We're mixing some unknown amount of 10%. That's your 10% right there, folks. And of some unknown quantity, let's call that x. Add that to a 30% acid solution, let's convert that to a decimal, of the remaining amount of liters. Now remember, we want 25 liters. Part of it is unknown. The other part is found by subtracting from 25. So think about that for a second. That 30% is multiplying with the 25 liters minus x, the unknown from over here. That's how those are linked. Because in the end, when you add x plus 25 minus x, you're back to 25. And that is the setup. If you grab your calculator and multiply 0.15 with 25, you'll get 3.75 equals to 0.10x plus, let's apply the distributive property here. You'll get 7.5 on the calculator minus 0.3x. The rest is undoing operations, combining like terms. Now, we have a couple of x's on this side that can be combined together. You don't have to move them or whatever. 0.1x minus 0.3x is actually negative. Okay? So keep that in mind. So negative 0.2x plus 7.5. I know, decimals are fun, aren't they? We can go ahead and make everything positive after we move the 7.5 to the other side. I'm now undoing operations. 3.75 minus 7.5 is negative 3.75. That equals a negative 0.2x. Yay. Make it positive. And then finally divide by 0.2 to both sides. And here we go. X equals to 18.75, and in this case, liters. Keep in mind, they might want the other answer as well. This 18.75 liters is of the 10% solution or acid. To get the other half, the other answer, you just subtract 18.75 from 25. And you'll get, let's do the math this way, 6.25 liters of 30% acid. So there they are. All right. All right, we're going to go to the next page and skip those examples. They will not be on the final. You're welcome to just cross them out. I usually like to draw a little balloon to indicate that we don't need them for the final. And I'm just going to skip those. Let's skip to the last page then. And what I usually like to do is work on the right-hand column and just do the problems with my students. Starting with number 5, we're going to solve each problem. The variable in this case is b. Draw your vertical line to separate the equation in the 2 spots. I have 4 times and plus 14. Keep in mind we're doing, please excuse my dear Aunt Sally, backwards because we're solving. All right. We need to get rid of plus 14. I'm going to go ahead and subtract 14 to both sides. And we have, whoops, 4b equals 8. Yay. Divide by 4 to both sides, because that's your inverse operation. Those 4's go away. B equals to 2. Nice. You can always do a quick mental check. Let's take a look. 4 times 2 is 8. 8 plus 14, it works. Next problem. Again, look for the variable. We need to move everything away from the variable. We have a negative 6 times k. Be careful here. It's not negative 6 like minus 6. It's negative 6 times k minus 3. We need to get rid of the minus 3 first because we're undoing operations. Let's add 3 to both sides. We're left with a negative 6k on the left-hand side and 39 plus 3 on the right-hand side is 42. Oh, that's nice. I know 42 and 6 do go into each other. Divide through by the coefficient, negative 6 to both sides. And be careful here. Something to keep in mind and keep track of negative and positives. We have a positive divided by a negative is a negative 7. Great. Number 7, we didn't have an example necessarily, but you have a couple of choices here. Some kids might just start cranking it out and undo operations. Let's do that first. I'm actually going to write that problem again on the right-hand side and show you there's more than one way to solve that problem. And you decide which one you feel more comfortable doing. Okay? All right. So the variable x is buried way inside the parentheses there. We can't reach it. It's kind of like those bloomin' onions at Outback. You know, you can't get to the center until you peel off the outside layers first. In this case, I have a 15 that's itching to move to the other side. Let's go and subtract 15 to both sides. That leaves me with, and be careful, there's still a negative sign right there in front of the 2. And 46 minus 15, of course, is 31. Next step is to go ahead and divide by negative 2. Now, some of you might be thinking, hey, should we distribute the negative 2? You could. I was going to do that with the other side, but I want to do this one this way first. Let's go and divide by negative 2 to both sides. We will get a fraction. Ouch. Very ugly. I'm still going to keep going. I'm going to subtract 3 next. Wow. This is much harder than it looks now. 31 over negative 2 minus 3. And eventually I have to divide by negative 2 as well. Oh my gosh. So I'm going to leave that alone and just say, oh no, complex fractions. Would the problem fare better if we distributed the negative 2 early on? Let's try that. So negative 2 times 3 is negative 6. Negative 2 times negative 2x is positive 4x. Watch out for those negatives and positives. Clean up 15 minus 6. Those are like terms. They can be combined together. Great. That's 9. All right. We're now going to go ahead and combine, undo operations, subtract 9 to both sides. That'll give us 37. All right. And divide by 4. This was a lot easier, wasn't it, class? 37 to 4 cannot be reduced. I don't really care, but you can leave it as an improper fraction. If you want to change it to a mixed number, reduce, that's fine too. 4 goes into 37 9 times with a remainder of 1. All right. One more example, we'll call that a day. Example 8. All right, here's the thing with this problem. We have fractions. There's a cool trick we can apply to fractions inside equations. The trick or the shortcut, when you have fractions in an equation, is to multiply by the least common denominator, okay? It's a cool trick. Even teachers are not fans of fractions. Take a look at the denominators. We have 5 and 3. And between 5 and 3, the least common denominator and some of you probably know this already, is 15. This is one way of looking at it. The old school of finding a least common denominator back in elementary school. Oh, there it is. 15 is the smallest multiple of 3 and 5 that we're going to multiply everything by right now. So 15 out here multiplies everything from the original equation. 2/3 y minus 2/5 equals to 5. Remember, we're going to be distributing the 15 to all the terms in the equation. Here, here, and there. And the reason why we do that is because 15 will reduce the denominator and make it go away. So for the first half, 15 and 3 reduces to 5. Let me write it out for y'all. Sorry about the small type here. But look what happens. Hey, look, yay. The denominator, 3, goes away with the 15 right there. 5 times 2 is 10. Let me write it over here. It's kind of cramped. Minus, over here in the second term, I have 5 goes into 15 3 times. 3 times 2 is 6. Equals to 15 times 5 is 75. So that's a cool trick to get rid of fractions if you're not very happy with that. The rest is undoing operations and solving for y, the variable that's what we're trying to solve for. Add 6 to both sides. Oh, another fraction. Divide by 10 last. Whoosh. All right. That is reduced It's an improper fraction, but if we convert it to a mixed number, then it becomes 8 1/10. Well, thank you very much. Hope you guys enjoyed that. I'm going to go ahead and stop sharing here.